wonderful. It was breathtaking. It was inspiring. The man had such a sharp mind. I said afterward, I said, who the hell is this amazing person? This has just been a wonderful talk. And they say, you don't know, you never heard of him. He is the person who shares the office with Crick, of Watson and Crick. So Crick is better known, but Sidney Brenner was sort of half of Crick, of Watson and Crick. So the story is this. Crick was the mastermind, the strategist, the general who led the troops creating molecular biology. He was a theoretician. He would read all the papers and he would see patterns and he would suggest lines of research. And Crick could not work alone in an office. He needed to have somebody in the office to talk all day long, to kick ideas with all day long. Otherwise, he couldn't function. And originally, this person was a young American called James Watson, who was much younger than Francis Crick. And you all know that worked very well, sharing an office. But for some amazing reason, Watson decided to go back to the US. I've never been able to understand why. So now Crick was in trouble. He couldn't function anymore. So he needed to replace Watson. And Sidney Brenner was a replacement. And Sidney Brenner stayed many, many years there, but eventually, since in a way he was under Francis Crick's shadow, eventually he emerged and did some famous work for which he got the Nobel Prize on the nervous system of an invertebrate. So he decided to go off in his own line of research. But for many, many years they shared an office. So what I'm proposing, Sidney Brenner is still alive, thank God. Maybe he'll say that I'm getting it all wrong. But what I'm proposing is, you see, when Watson and Crick discovered the molecular structure of DNA in, I think it was 53 or 54, you knew that it was an alphabet of 4 symbols, right? A, C, G, and T. But you didn't know what the language was like that was written with those 4 symbols. But you see, because of this flow of ideas, somewhere in the back of his mind, Brenner knew that these were instructions, it was software. And I think this helped to guide the work elucidating in detail the information flow and mechanisms in the cell. That's what I'm proposing anyway. So there's this hidden connection from Turing to John von Neumann to Francis Crick that emerges really from an autobiography. Well, it's an interview. It's an autobiography of Sidney Brenner, which were all interviews that were taped and then transcribed. And the reason I got my hands on that autobiography is because there was a biography of Crick that in one paragraph mentioned John von Neumann. And then I said, aha, there may be a connection here, so I have to get the autobiography of Brenner and see. And when I got the autobiography, I said, I hit pay dirt. I can make a case for this flow of ideas. Anyway, the way it works is, as Borges says, you create your predecessors. You know, this is maybe not the real history of what happened, but it is the rationalized history. It's the how do you say? It's the, history is always a lie, right? It's a simplified version saying how things should have happened sometimes rather than the way they did happen. Okay, so this is molecular biology, where I'm claiming that these ideas of von Neumann are there, and the key person to make this case is Sidney Brenner. Now, what about metabiology? Well, that's it's only 3 years old. Virginia and I have been working on this for years, and it only started to really work a year ago. And if you have to create a history of this, I would say the 2 milestones were, John Maynard Smith is a wonderful population geneticist that I was lucky enough to be at a meeting with north of the Arctic Circle in Sweden and to drink beer with. There wasn't much to do. It never got dark, and there was no place to go, which was wonderful because we all fell in love with John Maynard Smith. Everybody that I know, such as Richard Dawkins, whom I don't particularly like, but Dawkins also admires John Maynard Smith. He says, if you want a meeting on biology to be a success, all you have to do is invite John Maynard Smith and make sure there's a place to have beer. And then all the young researchers will congregate around Maynard Smith, and they'll all be inspired, and they'll all rush back to their labs full of new ideas. So John Maynard Smith is just wonderful. And There's a book of his in 1986 called The Problems of Biology, Oxford University Press, where in the first chapter, John Maynard Smith discusses how to define life. So he says the normal definition of life, the sort of obvious definition, is something is alive if it, if it takes in nutrients, excretes waste products, gets energy out of the nutrients, maintains its structure, and reproduces itself. So this is sort of metabolism plus self-reproduction. So that's sort of the obvious definition, says Maynard Smith, but it's wrong. Why is it wrong? Well, think of a flame or a fire. A flame is, while the candle is burning, it gets shorter, we get older, but the flame is a sort of metastable flow, and it can certainly start another candle. Forest fires can spread; they're self-reproducing, but they're not alive. Why? Fortunately, because they can't accumulate hereditary information. A fire does not remember its parents or its one parent. It doesn't remember how it was started. It doesn't accumulate genetic information, therefore it can't evolve, fortunately. So fires don't get smarter and smarter, which is, right? So this is the definition of life that I'm using in, well, I haven't quite gotten, so what is the right, okay, so the flame refutes the natural definition, shall we say, of a living thing. So what is the right definition? Well, Maynard Smith says the right definition is something is alive if a system is alive if it evolves according to Darwin's theory of evolution. In other words, if there is hereditary information, this is sort of assuming that Darwin's theory is right. If it has hereditary information, if there are mutations and there's selection and the system evolves. Now this may sound like a vicious circle. If I'm trying to do a mathematical theory of biology, if I take this as my definition of a living system, you may think, well, then obviously Darwin's theory will work. Well, that's not exactly the case, because you see, from a mathematical point of view, the first thing you've got to do when you have a definition is prove that it's not vacuous, which means that there exists something in the world of pure mathematics that satisfies the definition. So what I'm really doing with metabiology is constructing a life form that I can prove evolves. And it's a mathematical life form. It's a Pythagorean life form. It's the simplest form of life I can come up with that will provably evolve. It's the simplest mathematical structure I can come up with which provably evolves. Okay, so that's the challenge from a mathematical point of view. And that happened just about a year ago. Is that correct? Something like on the order of a year. Okay, so this was the breakthrough in metabiology when Virginia and I begin to feel that maybe there's something here, maybe this is a good research direction. And Professor Martin-Delgado had not yet written his paper, so that also is, the more work there is in a field, the more one begins to think that maybe it's actually an emerging field, an embryonic field. Okay, now a comment that I made before is, what kind of a mathematical field is this proposed new research direction? Well, it's using very different mathematics than Turing used in biology and the population genetics used. We're not using continuous mathematics. What biology is really all about is information and creativity, and that I like to refer to as postmodern or post-Gödelian, actually post-Gödelian and post-Turing mathematics. It's this kind of mathematics: algorithmic information theory, computability theory, complexity theory, computer science. In a way, if this point of view is correct, anytime you do theoretical computer science, you are in a way sort of doing theoretical biology, because you're studying software, the power of software that is maybe not the same as DNA, but it's in the same spirit. They're both universal programming languages. So these are the tools that I think, in particular, these tools were really all available. The tools I'm using in the technical paper were really all available in 1975, when algorithmic information theory fell into place. The structure conceptual structure. So this could all have been done in 1975, and I'm sorry I took so long to realize it. Because all the other stuff here is older. So when I'm talking about complexity theory, I'm really talking more about, so this is time complexity here, right? And this is program size or information content, but I'll sometimes use complexity for this. Okay, so now let me go in. So this sets the general framework, the general approach, but let me now go into the particular model that I study mathematically, and it's just a first cut at doing a actual, well, let's leave it like that, I guess. Okay, so the question, so this model is going to be really a very, very simple model. A biologist doesn't know whether to laugh or to cry. You know, they say, where is metabolism, where are ribosomes, where is this, where is that? And you know, that is a problem. On the other hand, you can look at it as an advantage. What it means is you can get evolution to work, you can get life to happen with a very, very simple system. Okay, that's one way to look at what this is. So you can take the flaws